Well, it looks like we can get started. Welcome back, everyone, and welcome back from the break. I hope it was a relaxing break for everyone. If you had to be working on getting caught up like I was, then I hope it was productive as well. To those students that were getting caught up on homework, I appreciate your work ethic. I know doing homework on the spring break is not the funnest thing in the world, but that's going to give a big impact on getting through the last 6 weeks of the semester. So we are on week number 11. And it's going to be kind of an ordinary week. We're going to work through chapter 19, begin chapter 20, but it's going to be kind of a slow start getting back into it after the break. I do have a dentist appointment that landed on Wednesday. It's not going to be a fun one. This one's a root canal. So I have to cancel class meeting and office hours on this Wednesday. But I don't anticipate any other random appointments like this one coming up in our last remaining 6 weeks. So we're going to jump back into chapter 19, but any questions or comments at all, folks, before we get started? Okay, well, let's get back into it. And again, welcome back, everyone. It's kind of hard to return right back into statistics after possibly not doing any of it for over a week. But what we were working on in chapter 19 is looking at how to do statistical methods, both confidence intervals and hypothesis testing, now with categorical data. We did one confidence interval procedure called the large sample confidence interval procedure, and we're looking into a modification of it. Sometimes it's not easy for those conditions to pass in the large sample procedure for a confidence interval for a proportion. And so we looked into the +4 estimate. This is the procedure that we left about 2 weeks ago, last Thursday, last couple of Thursdays. The idea with the +4 estimates is that it drastically changes the conditions. The sample size has to be just at least 10. So if you have 10 pieces of data and that's it, then you can run this procedure. It doesn't have to have any number of successes, any number of failures. So these could be all 10 successes, all 10 failures. The turnaround on this, or the drawback about the procedure, is it tends to have a very wide margin of error. But it's nice that if you have a small set of data, you can at least give that margin of error and estimate it nonetheless. The adjustment we make is right here. We're trying to widen out this confidence interval if the original procedure conditions weren't met. We widen out the confidence interval by adding 2 successes, that's the +2 here, and 2 failures, so that the sample size is artificially inflated to a sample size +4, which is where the namesake comes from in the +4 method. Then, when we make this new statistic here, the confidence interval for the unknown proportion of successes P is just the statistic, add or subtract the critical number Z star, same number as before, and multiply it against a new standard error. The standard error looks pretty much the same thing as before. We have P tilde instead of P hat times 1 minus P tilde. But that's the easiest spot to miss whenever you're running through this. Your standard error can be quite a bit off if we don't recall to divide by n+4 in that spot as well. So that's our warm up so far. This is the procedure we are just about to look into, analyzing our next set of data in example 5. Any questions or comments about it? Okay, well, here's the refresher on the context, what we're actually analyzing with this procedure. We were looking into the statistical study of a total hip replacement, ceramic hips that had been installed between the specific years of 2003, 2005 rather. This had a sample size of 143 people with the ceramic hip replacement. And out of that, we had X, that's the number of successes, 10 successes altogether, where success is the outcome that you had the ceramic hip installed and it developed squeaking. So again, that's only 10 successes. There's 133 failures, but with just 10 successes here, we actually can't analyze these data whatsoever using this procedure. The large sample confidence interval for proportion, large sample is really a big emphasis here, requires inside the sample that there be at least 15 successes and 15 failures. So we're way under with just the 10 successes right here. And this is a typical big problem with analyzing categorical data. Whenever the incidence of the occurrence, squeaking a hip, is really small, like in this case, or for studying an incidence that happens very, very often, a proportion closer to a 1 instead. So we check the conditions on this one. The conditions were pretty easy to run through. We're going to mention our conclusion, the sample wasn't random. I should say that better. We don't know necessarily that the sample wasn't random, but in this one sentence write-up of the context of the study, no randomization was mentioned. So we'll mention that shortcoming in our conclusion. But our confidence is at 99%. It had to be just at minimum 90%. The sample size had to be at minimum 10, but we're way ahead of that at 143 individuals. And so we can now analyze these data. So we're going to look into the formulas that we started out with. Here they are down on the paper. Then once we have that, the interval is going to be easy to build, just like what we did on all of our other procedures. And we'll give a conclusion relative to what we said our parameter P was here. Any questions at all, folks, before we finish up the analysis on this one? Okay, so here's how the last steps on this one goes. First, we want to calculate our new statistic, not p hat, the p tilde, tilde being that symbol right there. We're going to take the number of successes. Let me scroll up a touch. It was 10. So take 10 plus. We're adding 2 to that. So 2 successes have been added to the sample. To balance it, we're adding 2 failures. So we go to sample size n, which is 143, and add 4. We looked into last class 2 Thursdays ago what this effect is. Overall, what this does is makes the standard error bigger, which is going to widen out our confidence interval. So now when we say in our conclusion we have 99% confidence, that becomes a much more honest statement altogether. So I'll leave this just as a fraction, giving it a more exact expression. We have 12, 147. And then next thing we compute is the standard error. I'll round this one to 6 decimal places. So really all this is just a couple of substitutions, calculator operation, and we'll be ready to build the confidence interval. So the format is going to be, depending on how you write this out, I'll keep it in this kind of sideways format. 12, 147 times 1 minus 12 over 147. Divide that entire quantity by 143 plus 4, or just 147. That's a good idea to always kind of eyeball these kinds of things before you do throw it into the calculator. One way you can tell everything is about the way it should be is these denominators, 147, 147, and 147 again on that spot where the red dot is, tells us we're using the formula the way it's intended to be used. Now we're just going to throw this into the calculator, do our lower bound, upper bound computations, and we'll be on our way with this one. Any questions at all, folks, to this stage? Okay, let's throw this in. Guess we can kind of minimize this just a little bit. Okay, there we go. So first thing, I'll go square root 12 over 147. If you're using RStudio as a calculator, make sure you type that times there literally, or it won't know what to do with just putting the fractions together like that in a standard calculator. Then go 1 minus 12 over 147, then divide by 147. And in this format, no order of operations kind of issues. We get our standard error, 0.022583. Okay, it's probably a good idea with 6 digits to just double check that. 0.022583 upon rounding. So we've got it, folks. That's our standard error. And now for the +4 method, all we do next is write out P tilde, add or subtract, A critical number Z star, which looks like we've pre-computed here. Multiply that against the standard error we just found for P tilde. We make a substitution, well, a couple substitutions, and form in the spot for P tilde, we have 12 over 147. Add or subtract critical number 2.57583, which came from our confidence level, and multiply that against the 0.022583. Then I'll put a little right arrow here that says this interval here will imply something. The something is P is now going to be contained within two bounds, a lower bound and an upper bound. So we're going to place this in the middle by computing out these values. Let's throw that in the calculator, see what we get. Let me know if any of my numbers go sideways. I've got 12 over 147, lower bound first, 2.57583 times 0.022583. Kind of an interesting coincidence with the 583s. So on the lower bound, now that we're at this final computation, I'll round this to 4 decimal places. We're at 0.0234. Let's make that 0.0235 upon rounding. And last, swap this for a plus here. And we're at, hang on, that looks like something went wrong. I think I threw a 3 in there when I tried to plus it. 81%. You know, the margin of error can get pretty wild like this one. If this was the real interval, then you'd have to wonder if it had any use at that point. And that could potentially happen if, say, the sample size was very, very small. But that's a bit extreme in this problem, so let me fix that. Okay, that 3 threw it off. And that's about more in line with what I was expecting. Still a huge margin of error, but not that big. It's going essentially between 0 and 100%. Our confidence interval is essentially useless at that point. So 0.1398. And at that point, we're completely done. That's our new confidence interval estimate. Any questions at all, folks, getting to that last step here? Okay, we mentioned last couple of weeks that when you go to write out your conclusions, you have a lot of freedom in how you decide to write these things out. Just like when we're estimating categorical data, you might call this the true mean, or if you prefer to say average, I would say that's completely acceptable as well. You might say the population average. And same kind of issue here with categorical data. In our first example, we call this the true proportion. But if you prefer to write this out as a percentage, you could say the population percentage or the true percentage. Because we went with percentage here in indicating our parameter, let's convert this over to an actual percentage just to match up the language. And now we can say we're from 2.35%, bounding the true proportion P, or percentage, up to 13.98%. Now we'll give an interval, or excuse me, a practical conclusion of this interval using those percentages. And this is the stage at which it feels kind of formulaic. The algorithm for doing all these confidence intervals, every single one we've done in the class so far, has been just about this. Find the value of the statistic, find the value of the standard error, get the critical number, put your parameter in the middle, format it differently if you prefer, but once you've done that, here's what the conclusion looks like essentially each and every time. We recall the level of confidence we were taking. This one was a 99%. Let's double check. So we'll begin by saying that. You could say that at the end if you prefer, but I say it at the start just to make sure I don't forget it whatsoever. So let's begin with 99% confidence. When it says a practical interpretation, we mean interpret that interval. When it says using the context, what it means there is we're not going to say P between 2.35%, 13.98%. You have to say exactly what P is, the way we indicated it in part A. So we'll say with 99% confidence, their true percentage of all people with a ceramic hip replacement, I'll say with ceramic hips, installed. Again, there's probably a better way to put a word here. Installed doesn't really sound people-centric, but let's keep it the way we indicated before. Hips installed between 2003 and 2005 that developed squeaking now that we've read out P, we'll just say is between those two bounds, is between a low incident of 2.35% and as high as getting close to 14%, 13.98. So that's our final conclusion on that one. Again, we probably could have finished this 2 Thursdays ago when we were running through it, but we didn't want to rush to get through this kind of problem. I'm glad we took the time to just kind of come back to it, refresh on the procedure, and finish it off today. Well, any last thoughts, folks, on concluding with this one? Okay, well, if you ended just like this on a homework problem, even an exam question, I would say that would be just fine. I wouldn't be super picky. The things I'm really picky about are we have to make sure we're definitely using the context, mention the confidence level, the bounds that we were between. But one thing that might feel kind of satisfying is when you do these kind of problems, when you work through the condition checking, we're trying to see if the study was done appropriately. And again, we're not trying to read everything we can about the study. That's extra research going above and beyond the class. As a classroom question, we accept that this is all we know about the problem. It doesn't mean randomization is not met. This could have been random data, but it's a big unknown based off the information was provided. So it's good to come back to this. If there's any shortcoming in the data, if it's quantitative and it's highly skewed, we should mention that in our conclusion. Or if we are missing information on randomization, we should mention that as well. So to wrap up this question, the last thing I'd probably mention is, since it is not known if the 143 individuals came from a random sample, our conclusion may be challenged. So if they messed up the sampling design really, really badly, then doesn't matter how nice the statistics looks, everything we said here in the conclusion is possibly totally incorrect. It might be right just by chance alone, but we can't say the statistics would support it at that level. But we did it, folks. That's our first look into categorical data, estimating a parameter, just a single parameter. In chapter 20, we'll redo the confidence interval method when we're looking into a difference of two parameters. But before we get there, we have to look into what about hypothesis testing? And again, it's kind of a nice refresher on everything we've done in chapter 17 and 18, even chapter 14. So we're going to take another look into hypothesis testing, see how it goes for categorical data, and then look at two independent populations in the next chapter. So here's our rundown for the hypothesis test procedure. First thing we do is we cite the central limit theorem once again. This is the one that the confidence interval procedure is based upon, and same idea with the hypothesis test. And another thing to come back to is, recall whenever we're doing a hypothesis test of any kind, the logic is kind of interesting. We make an assumption first that the null hypothesis is true. Then we look at how extreme our data is and compute the probability of getting data as extreme as ours under the assumption the null hypothesis is true. That's finding the p-value. That p-value is really, really small, then we're going to challenge that null hypothesis, reject it in favor of the alternative. But this being the first step of hypothesis testing, assuming the null hypothesis is actually true, has different kinds of ramifications depending on the data you're measuring. So let's refresh on what's going on with this central limit theorem. Here, we have a random sample of size n. The sample size is manifest here in the standard deviation portion. We're looking into the population proportion of successes p. That's a parameter that we're measuring. But to do that, we compute the statistic. That's going to be p hat, the sample's proportion of successes. And that p hat comes from a normal distribution that's distributed in this particular way. The center, the mean of this normal distribution is p, and the spread, the very standard deviation is better to say, not variability. The standard deviation is this structure right here, which is what we based our standard error off of. This normal distribution is an approximate one. We say that's right here, but the approximation is excellent in just about any context if these two inequalities hold. If the expected number of successes and expected number of failures are both at least 10. So that's our refresher on the central limit theorem. And we did an actual full-on example 1 where we use this directly. Hypothesis testing is almost in a real sense kind of redoing example 1. So here's our really fast example just to see what's going on. Then we'll do a full question with actual complete context. It says, gather a simple random sample of that size, 1024, from a population with true proportion of successes p. Our challenge here is if we're doing a hypothesis test, it's because p is unknown, which means everything here is also unknown as well, except that you do this as your very first step in conducting the hypothesis test. You assume that this null hypothesis right here is the literal truth of the population. That's a humongous assumption. Once you assume the null hypothesis is true, you put a value here for p at even more. We've placed a value here and here for p as well. Suddenly we have the exact sampling distribution for p hat. So that's exciting news. The model is completely and utterly known in hypothesis testing, assuming the null is true. So the question says, assuming the null is true, what is the sampling distribution of p hat? We can say p hat is distributed. Normally, it is an approximate distribution, so those two conditions have to hold. But the good news about it is we assumed a value for p right here. That's the unknown population proportion of successes, and we're assuming it's exactly 0.35. So we have a value in the center, and even better news, that's supposed to be a comma. Let me fix that penmanship. We have the complete description of the standard deviation. So we'll take 0.35 here, 1 minus 0.35 or 0.65 if you prefer. We divide next by the sample size. In this problem, it's 1024. And that's our complete model. This entire part right here we'll refer to as SD, to stand for the standard deviation of p hat. And standard deviation of p hat is completely known. This means there's no standard error whatsoever in the hypothesis testing problem, which is kind of strange when you think about that. When we looked at how we did the confidence interval, we did p hat plus or minus a z star times standard error of p hat, or the p tilde was the same formula or format. We use a specific standard error, but that's because we never made any assumption whatsoever coming from a null hypothesis. When it's just a confidence interval procedure and nothing else, there's not as much leverage like we have here. That's why we needed the standard error. I noticed I messed something up here. Let me see if I can fix that. There we go. So since we have the standard deviation, our test statistic is going to look a lot different. We won't use a standard error whatsoever. Any questions at all, folks, with the example 6 derivation? Okay, again, this is the portion at which categorical data starts to feel really pretty weird. Say if you were in chapter 14, we were about to do a hypothesis test, you would take a z-test statistic, you would take an x bar minus a mu naught, divide by, say, a standard error in chapter 17. But in this chapter, we don't do that whatsoever. We're going to use this exact value here, which again possibly looks a little bit similar to chapter 14 because we assumed a value for sigma, but that was an unrealistic assumption. That did not come from the null hypothesis whatsoever. But our null hypothesis is powerful because that's just a one parameter distribution. So now let's take a look into the whole method. We have conditions, but these conditions are new this time. Well, the part 2 right here that's highlighted. Just like before, on condition 1, we'll briefly discuss whether we know the data is random from the information they gave us or if that's an unknown. Condition 3 is about the same. The population has to be larger than the sample. If that's not true, we lose independence in the problem and the normal distribution does not apply. But we're using the same exact rule of thumb here. To really address condition 3, you have to be an expert on the demographic you're looking into or the biology of the actual animal you're researching and so on. So again, we're not meant to do an entire research project to check condition 3. We'll just go based off what we can understand on what the problem gives us. So also briefly discuss this as well when we're checking conditions. But condition 2, we can do this one rigorously. We'll show the counts of n times p naught, n times 1 minus p naught. But let's take a look at those counts in view of what we did in the confidence interval procedure, because this is quite a bit different. Again, categorical data has lots of little tiny subtleties we have to watch out for. When we were doing the confidence interval procedure, we looked into the number of successes and failures in the sample itself. And that's the formula, n times p hat, n times 1 minus p hat for successes, failures in the actual sample. But this is different. If that p naught grabbed your attention, then good on you. You have a careful eye. This is not the number of successes and failures in the sample whatsoever. In fact, it doesn't matter how many successes or failures we have in the sample. We're looking into expected number of successes and expected number of failures when we make the assumption that the null hypothesis is actually true. We're assuming that this holds as our first step in hypothesis testing, and then we say, if the null is true, we gather a sample of size n, how many successes would we get? That's the expected number of successes formula, and same for expected number of failures. Both have to be greater than or equal to 10, just coming right off the central limit theorem statement for their boundary there. So those are the things that are new, the things to watch out for. And then for the test statistic, we take the difference from the data, p hat, and the assumption you made in the null hypothesis, p naught. Then you divide by this p naught times 1 minus p naught divided by n. But that's the actual standard deviation coming from the normal distribution that we saw in the last question. So what this whole test statistic z is measuring is the number of standard deviations, not estimated standard deviations, the number of assumed exact standard deviations. Let's make that plural, standard deviations that p hat, our sample data, is away from p naught that's coming from the null hypothesis when h naught is true. If that's a lot of standard deviations, say like 4, 5, 6 or more, then that's going to happen very, very rarely. The p-value is going to be very small, and really just two things could have happened. It means Either the null hypothesis is false, we have such a large test statistics, huge number of standard deviations, this assumption is possibly just an error, or a very unlikely rare event could have occurred. Repeated sampling, or excuse me, repeated studies can eliminate the possibility of a rare event occurring, making that chance of it happening smaller and smaller the more we replicate the entire study. But we're going to look into, if this is a very large test statistic, how small the p-value gets using the same decision tree right here on a benchmark of evidence, the significance level alpha. So just redoing once again what we did in chapters 14, 17, and 18. So that's the logic of the hypothesis test for categorical data. A lot of it is very, very similar, but the way it gets put together, in particular that test statistic, does feel different. So watch out when you're doing this kind of problem. If you do the standard error here, like in confidence intervals, we could lose a good amount of credit on that particular question. And also be careful checking the conditions. We have to show what the samples, their numbers are for expected failures and successes. We can't say how many failures or successes in the sample to check that condition there. Well, any last thoughts or comments, folks, before we take a look at the p-values just for review and then run through a new problem? Okay, and we've looked at these diagrams before when we were in chapter 14, chapter 8, 17, 18 as well. Let's just put them down for just a quick review. If we're doing a right-tailed test, then something in the data is going to indicate we're looking for the statistical evidence that the parameter is larger than some hypothesized value. We compute the test statistic z, and we get the p-value, let's say z is here, by finding this area. And our syntax for this, again, we're doing this just for the sake of a review, highly similar to what we've seen before. This is going to be p norm. We throw in z, no degrees of freedom whatsoever on this, and we just say lower dot tail is false. So that's our p-value in that case. If it's a left tail test and the research question has indicated that directionality, then I'm just putting down a random z for the sake of the diagram. This would be our p-value out here. So here's z, and to compute this area, all we write down is just p norm z. So really short syntax. Then finally, the default test is the two-tailed test. So if we're just checking for a difference in any direction in the research question, then we go a little bit fancy. Here's how the author does this one. You're going to have, say, z here. There's two possible diagrams. I'm assuming the test statistic came out positive. It could have came out negative, and I would have to say negative z here, double negating to force it positive. So if there's our z there, then symmetrically across 0, here's where negative z is going to be. And our p-value is both regions at the same exact time. So this p-value is twice as large as the p-value in the left tail test and the right tail test. And we compute it by saying p norm, take the absolute value of z so we don't have to worry if it's positive or negative, double either the left tail area, our author didn't go that route, or double the right tail area. And if you're going to double it, don't forget to put a 2 there, as I almost did. Let me start over so this fits in a little bit better. Go 2 times p norm, absolute value of z. And since we're doubling the right tail area, just to keep the formula similar to the reading of the book, we would have to say lower dot tail is set to false once again. But don't forget this part's right here for the two-tail test. Well, we've got it, folks. That's the total description of the hypothesis test. There's lots of different kind of moving parts, but we'll walk through them all over again as we go through the next problem. Once we get the p-value, this decision tree has been identical since chapter 14. We'll compare it against whatever the significance level is stated to be in the problem. And if one isn't stated, we'll state our own to match the problem. Any last questions or thoughts, folks, before we go to a top to bottom hypothesis test? Okay, well, let's try this out. Here's our new context. And this one looks to be very, very, very serious medical data. So I'll go through this carefully. Some of the words here are pretty interesting. You could Google them to learn a little bit more about them. It says in the article, prothrombotic factors in children with stroke or porencephalopathy. I had to look into what this was because I wasn't sure personally. That turns into be some kind of cyst or something in the brain that could be caused by an infection, some other kind of defect, or sometimes even seizures in very, very young children, newborns and such. So we're looking into these kind of factors. This is the name of the study. In the study, these set of authors compared differences and similarities in children with arterial ischemic stroke and porencephalopathy. So again, pretty serious and heavy data, so we'll treat it appropriately and give the best analysis possible. This says that there's 3 classification categories were used. And that might give some alarm bells because we mentioned at the very top of these notes, in this entire chapter, the idea is we are looking into, see, where was I trying to go? I guess the very top. We're looking into categorical data where there's exactly 2 outcomes, a success and a failure. This problem says it has 3 outcomes, so it almost doesn't seem like it actually fits this chapter. It kind of looks like a chapter 21 problem. But the concept with these particular data is, even if there was 3 outcomes or 4 outcomes, you can still turn them into successes and failures. You'll be focusing on just one outcome as your success, and all the other outcomes that could be 4, 5, 10 categories, those are your failures in the problem. So if that's the way they want to analyze these data, chapter 19 can still be used, like in this example. So again, that's a bit of a warning sign when you see this kind of problem out in the wild, mixed in with other questions. But what they say next is going to tell us how the data is actually going to be analyzed. We're being told the 3 classification categories were perinatal stroke, delayed perinatal stroke, and childhood stroke. Next, of the 59 children, well, we have a sample size, so we can record that in the margin. And it's 59 children. We're told 25 were diagnosed with delayed perinatal stroke. This makes it seem like the study is really focusing on that one category. That's the major part of the study itself, is to investigate that outcome. So even though there's 3 classification categories, this looks to be the success, and the other 2 would be considered the failures in the study. But that depends on what the research question is. So the research question says, do the data provide sufficient statistical evidence to conclude that delayed perinatal stroke, so that's that category coming up again, does not compromise 1/3 of the cases among the 3 categories? So again, even though there's 3 categories, the research question is about this one category being the success against the other 2, now the failures. So that makes this, in fact, a chapter 19 question. We cannot use chi-squared on this problem based on the way the research question is being asked. So let's highlight this. A direct question like this one, not every single time, but sometimes for hypothesis testing, it's a dead giveaway. This is the alternative hypothesis. And this problem, that is true. This is the alternative hypothesis that we're going to be testing. When we look into it again, it says, do the data provide sufficient statistical evidence to conclude that delayed perinatal stroke, so this category with 25 successes, does not compromise? Well, that's not a direction. It's not saying is greater than or is less than. So these are keywords to say two-tailed test. And when it says 1/3 of the cases among the 3 categories, Well, that would be the hypothesized value. We would call it mu naught if we were dealing with quantitative data, but for categorical data, we call it P naught, and P naught is the value 1/3. We'll use that value in both the null alternative hypothesis. And next, let's say here, now that we've read through the context, these are the successes. And our author uses this special variable to count the number of successes. X is going to be 25 successes. So that's the readout of the context so far. Any questions at all, folks, looking into this one? Okay, it says, answer this question by providing a complete analysis. This one is going to be a hypothesis test analysis, and it'll be done at the 1% significance level. So maybe one last thing to indicate, once you see that, not a bad idea to just write down on the margin, write down in your notes somewhere, alpha is 0.01, because it'll prime your mind on how everything fits together. There's lots of moving parts in hypothesis testing. So anything you just write down on paper somewhere kind of gets it all into our subconscious so we can start working on it and thinking about it. It's a complete analysis, so we'll go through the standard 4 steps that we've been doing all along the semester. For this, we can put the practical question in our own words if we so choose to. If we want to directly cite something out of the problem, like we mentioned before, that's completely fine as well. Let's go that route. This seems to be the practical question. It's all our alternative hypothesis in words. So all we're doing here, usually this is worth something along the lines of 1 point, but it gets us started in thinking about what's the problem all about, helps us to write the parameter better and our overall conclusion a little bit better if we just do this one part here. So that's the state part of the problem. We've stated the practical question, we've used the context, and this absolutely requires statistical inference. For the next phase, we want to define what the unknown parameter is in the first place with the context, then state both null alternative hypotheses after we know the parameter. So that gets us back to this context here, really both paragraphs on the context. It's a good idea when you do these kind of problems to read the context probably multiple times to make sure we didn't miss anything small, any important detail. So here we can begin by writing out P. And like we've mentioned before, you could call this the population proportion, population percent, or true proportion or true percent, up to you how you'd like to word it. I'll go with just population proportion. P equals the population proportion. Now, here we really need to mention 2 things to get full credit on this kind of parameter. We have to say what the population is, and we have to also say at the same time, what are the successes in this context as well. Let's focus maybe on the population. There'll be the population proportion of all. When we think about the population, it's a good idea to kind of work backwards and think about what was the sample. It was 59 children, so we can say of all children. But that's too wide open as a population so far. We're not talking about all children. We're talking about children that had a specific condition. It said 3 classifications were used, or let's start maybe here. Of 29 children, 59 children, 25 were diagnosed with delayed perinatal stroke. They also had 2 categories of diagnoses. So we can write that in if we'd like. But let's maybe look into the article itself. It said in the article, we're looking at prothrombotic factors in children with stroke or porencephalopathy. I think that'd be probably a good way to word it. You could say all 3 categories here, but that's a pretty good paraphrase. So I'll say, we're looking into P, a parameter, proportion of all children with stroke, or porencephalopathy. I think I'm pronouncing that wrong. Porencephaly. I'm gonna have to work on that one. So all children with that condition, that After we have the population down, following the word that, we're mentioning what the success was in context. And these are the successes that were diagnosed with delayed perinatal stroke. Diagnosed with delayed perinatal stroke. Okay, we've got a parameter down. Any questions at all, folks, on that tricky step there? Okay, these, again, can be pretty tricky, but as long as you say you're talking about the proportion, not the average or mean this time, you've mentioned the population, you've mentioned what the success was, those are the three things that we would have to hit for this kind of parameter with categorical data. Next, we're going to state the null hypothesis, the alternative hypothesis, so this part, it's stated in terms of that parameter P. So we can now write, we will test. Let's write this out with some blanks just to think about this problem as we go. Once you write down the null hypothesis, that parameter is going to go here, and then give it a little bit of space, against. When you write down the alternative hypothesis, same parameter goes there as well. These are both statements relative to the unknown parameter P, and we'll say, give us a little bit of space, at alpha equals 0.01, coming from the significance level in the problem. Now, in our null hypothesis, I'll write equals, and that's where we go to the value that we're testing against, the hypothesized value, the thing that's used in essentially all of the formulas for the test statistic and so on, is right here, 1/3. They're asking if it does not comprise 1/3 of the cases. So the null hypothesis is a statement of no change, we're maintaining the status quo, and we're saying it is 1/3 of the cases amongst those three different categories. But here, we're asking if it does not compromise 1/3. This is the actual research question. They want to know if that proportion is higher than 33% or lower. It's a two-directional test, so we're going to use the not equals for the two-tailed test at 1/3, which means when we get to the p-value step, we have to remember double the p-value because of that two-tailed test there. And no harm in writing this in at this stage, just so we can be extra sure not to forget. Double the p-value. We've got it, folks. This is the complete write-up of what the parameter is and the hypotheses we're going to test. This is, again, the tricky part of the problem for sure, getting through these two steps here. The rest of it is kind of going through just the motions. Conditions is still working with the context, but not as heavy as we just did. And then after that, it becomes a math problem where we return back to the parameter on our final conclusion. So as far as conditions go, there's three big ones. Condition one is we're looking into any information that we might have had about randomization. And this was published in a very reputable looking journal. So there's probably was some kind of randomization here, or maybe they had a great argument of why the 59 children is a highly representative sample of the population. But based on what they told us in these two sentences, we just know 59 children were used in the study, no information on randomization whatsoever. So I'll just say here, it is not known because they didn't tell us if the data is random. Again, that doesn't end our procedure. This is something we can come back to and mention our conclusion at the very end. And now we move on to the next condition, which we mentioned is really, really tricky in a certain sense. It's not the same as a large sample confidence interval procedure whatsoever. Doesn't matter that we have 25 successes in the sample whatsoever, because we're doing this next. We're calculating the expected number of successes and the expected number of failures. So we have to work out this formula, n times p naught, and n times 1 minus p naught, or we can do a subtraction instead if we prefer. So let's work through this next step. This might be a handy screenshot just to put in as we are thinking about this. So we're going to measure the number of successes. Let me say this more specifically. The expected, not the amounts we found, but the amount we expect, when that null hypothesis right there by the red dot is actually true, will be this. Expected number of successes will be n times p naught. N is the sample size at 59 children. And when it says multiply it by p naught, it's referring to this right here, that 1/3, the same quantity that goes both in the null and in the alternative. So take 59 times 1/3. This next step is going to look a little bit weird, but bear with me. We're going to take 59 times 1/3, get to 19.7, I'll round it to. And these are in fact children, but we don't round to the nearest child. We keep it to something like this, rounding to 1 or 2 decimal places. Even though that doesn't seem feasibly realistic, you can't sample 19.7 children whatsoever. We keep that value because it's really a type of average. When we say expected number of successes, what we mean is repeat the study over and over and over again with the same sample size at 59. And if the null hypothesis is true, we'll see on average that many successes in all the studies. So it looks weird, but we keep it as a decimal for that reason. This is greater than or equal to 10. So we meet that benchmark there. But the number of expected failures has to also exceed 10. So let's write that number now. The expected number of failures, we can calculate with this formula as well. It'd be n times 2/3, but usually it's just as easy to take the total sample size, 59, minus the expected number of successes, 19.7, and get your number that way. So let's take 59 minus 19.7. We have 39.3, which is greater than or equal to 10. So we've hit both benchmarks. We're greater than or equal to 10 on both ends. So we can now give a conclusion. The sample size is large enough. I don't know why I put an exclamation, but let's stick with it. When you go to do this in your homework, be sure to show these values here and here. So these must be shown. Any questions on condition 2? Okay, condition 3, once again, is a hard one for us to check extremely rigorously without doing extra research, learning more about this condition. But what we can say is, if the sample size was 59, we have a rule of thumb that goes, the population must be much larger than the sample, but the population for our rule of thumb should be at least 10 times greater than the sample size. So at 59 children, unfortunately, these conditions are not ultra rare. So it's very feasible to say, even if the population is just children in USA, or especially if the population is all children globally, that definitely is not larger than 10% of the population. Again, we just briefly discussed this based off what we know. I'm not going to be super critical on condition 3 because it's a whole research question on its own, really. The authors that would have done the study, they would have probably have a really great idea about these kind of populations to address that condition a little bit more firmly. We'll say here, just to wrap up the condition checking, the sample size is very likely to be less than 10% of the sample size. When would this condition fail? I would have to give you a problem that says, with really clear context, this condition is ultra rare. I might have to even tell you in the context that there are only, say, 500 known cases. If you have that kind of information, then you can show that condition 3 would fail. But in our textbook, which is more kind of an introduction to all of these various statistical methods, that's going to be a pretty rare problem. We're really just looking into condition 3 to think about the total set of conditions. But we did it, folks. We've done a deep dive in the context, analyzing everything from these two spots, the plan and solve phase. Any last questions or comments before we do the computational side? Okay, well, here's, in a certain sense, kind of the fun steps to all this. Once we get all the way through here, the computations are going to look like this. First thing we want is the test statistic, but maybe even before calculating that, we want to calculate what we did in the prior example, number, I believe that was 6. We'll calculate the standard deviation of p hat. Again, not the standard error whatsoever this time. We go to the central limit theorem from proportions, and we're going to plug in that value 1/3. Because once again, the first step in hypothesis testing is assuming that this is true right here. If that's true, the standard deviation becomes square root p naught times 1 minus p naught divided by sample size n. So this is now 1/3 times 1 minus 1/3, or 2/3, divide by the sample size, which is 59. Let me double check. 59 altogether. Then we'll just throw this into a calculator. Square root of 1/3 times 2/3 divided by 59 gives us this figure, 0.061372. And again, that's a lot of digits to memorize coming back from spring break. So let me double check. 0.061372. Okay, so we have the exact standard deviation, assuming that's the literal truth right there, the null hypothesis about the population. If that's the case, we can now look into what are the odds of getting data as extreme as this out of 59 children, 25 successes. That should be our next step to calculate that p hat is x divided by n, which is just 25 divided by 59. So we'll calculate p hat, x divided by n, 25 successes divided by sample size 59. I'll leave it in its exact form. After we have that, here's our test statistic. It's labeled as z, since we're going to use the normal distribution for the p-value. It's the distance between what the study measured, p hat, versus what's assumed in the null hypothesis, p naught, divided by standard deviation, because at its core, test statistics are number of standard deviations. So let's measure this. That means this is going to be 25/59 minus 1/3 divided by 0.016372. So this is going to tell us how extreme our data is in terms of those standard deviations. So take 25/59 minus 1/3. Don't forget parentheses for your numerator to follow order of operations. 0.016372. And we've got, I feel like I made a mistake somewhere here. Let me double check this. 0.016372 for my denominator. I don't know why my numbers look a little funny there. Let me know if you see anything odd as I double check these. So I have a square root of a third times 2/3 divide by 59. I think I was okay with that square root. And then in my test statistic, 25/59s minus 1/3 that we're checking against. Standard deviation there. It looks like it's everything that we've got. For some reason I thought that that number seemed a little bit different. So altogether, it's about 5 standard deviations, 5.5213. For some reason, that just looked a little suspicious to me. Not too sure why. Well, any questions or comments at the moment, folks, with the computations? Okay, well, let me just double check one thing. Square root. If I go it like this, 1/3, I don't think that's the issue, but just to be really, really paranoid and make sure I've got the right standard error, let me write it in like this. And I had 0.061372. That looked about right. And to double check it one more time, 25 divided by 59 minus 1/3 divide by 0. Oh, I think I see my mistake. I'm going to chalk that up to coming back from spring break and just having a small issue there. I have 0.061 here, and my dyslexia was not allowing me to see that right away. I transposed those digits to 0.16. So when I was double checking, I was looking at this a little too carefully. So let me fix that there. That should have been a 0.061372, and that's going to make a big difference out of nowhere. So with that fix, 0.061372, we get that value. Again, that's a big difference. 5 standard deviations, that's guaranteed to be statistically significant. But when we go to the correct computation, 1.4729 standard deviations, that one's borderline, probably not significant. Our conclusion is going to look radically different. So 0.14729. I'll round that to a 3 there. Okay, double checking my digits since the numbers are not playing around nice. I got that decimal in the wrong spot. Let me try one more time. 1.4729. Phew. Okay, I think we got through that. Any questions so far, folks, with the revised numbers? Sorry if you're working in pen today. Okay, with the corrections there, we're finally ready for the p-value. It's a two-tailed test, so we're looking into the area in both tails of this one, which just means we're going to multiply our p-value by 2. So for the p-value, we're going to take 2 times, so there's our times 2, so we don't forget, p-norm. The formula says take the absolute value of z, but that's positive, so if you forgot that part, no harm done. But just for the sake of writing down a process for in case that came out negative, I'll write it in as the generic formula we stated in the notes. ABS for absolute value, 1.4729, then lower, dot tail equals false. So that will give us our p-value. One last computation here, take 2 times p-norm, absolute value 1.4729, lower, dot tail set false, and that's our p-value. That's quite large as far as p-values go. It's 0.1408. Our significance level alpha is at a 0.01, so we can say here, to organize our thoughts, this is greater than or equal to 0.01, which is alpha. That means our conclusions are going to say we are going to fail to reject the null hypothesis. We have to say what that means in context. It means we failed to find significant statistical evidence that that alternative right there is true. But we made it. We just now have to put a conclusion down on paper. Any last questions at all, folks, on that p-value there? Okay, again, really easy mistake to make on the p-value side is don't forget that ×2, since it was a two-tailed test. If it was a left-tailed test, right-tailed test, then we don't put in that part there. Now, just for the sake of an overall review, let's take another look in this table to see how we put our conclusions together. So these are the only two conclusions that we can give relative to a hypothesis test. We use this table as well whenever we're talking about a type 1, type 2 errors from before. Then we go back, look at how we defined our parameter, and specifically what we're interpreting is that alternative right there. So let's put this down as well. And here's what our conclusion is going to look like. Based on that p-value, it puts us on this end of the table. We failed to reject the null hypothesis, but this is what we're going to say in red. We failed to find statistical significant evidence that HA, there's our alternative hypothesis right here, is true. So here's our readout. This study failed to provide significant statistical evidence and then, even though it's optional, I think it's always a good call to mention at what level was your evidence in the first place. So I'll say here at the 1% significance level, to support the hypothesis that now finally, we've read out the thing that's in red. We can't say alternative hypothesis and call it good because we now have to say exactly what this was in context. Very similar to what we did with the confidence interval, but just a different format. It's not an interval this time. It's just an inequality that we have to read out. We're going to say P not equal to 1/3 or just 1/3 if you prefer. We have to read out one more time what P was in the first place in context, that parameter. So we have lacked the evidence to support the hypothesis that the population proportion of all children with stroke or porencephaly that we're looking at just one specific condition, delayed perinatal stroke, that were diagnosed with delayed perinatal stroke okay, we got through the P part, and now we have to just say is different from or not equal to 1/3 or 33.3 repeating or 33.3 repeating percent, however you'd like to convey it. I'll go with the way it's written here and just say is not equal to 1/3. And that finally wraps up the question. It doesn't mean we found evidence that this is true. We just lacked evidence against it. And evidence of absence is not evidence that this null hypothesis is true whatsoever. Our sample size was quite small. There could be a real effect, but we just couldn't detect it using a study with 59 children. Well, we did, folks. That's the wrap up of how hypothesis testing goes in this land of categorical data. What we'll be doing next is turning this all around and say, what happens if we're comparing two different populations? That'll be chapter 20. Or another thing we're going to look into in chapter 21 is, if this question was written just a little bit different, and we really want to consider all three classification categories at the same exact time, we'll look into the chi-squared procedures in chapter 21. It has to go with a specifically different worded question, but that could be a whole different new analysis we could give to these data. Well, any last questions or thoughts, folks, before we call it a day here, just a little bit earlier? Okay, well, as far as where we're at so far in the course, our chapter 19 is considered done, so this is a official due date for our assignment number 9. Our chapter 20, we're going to look into once we come back on our next week. So once again, if you missed an announcement, sorry for the class interruption on Wednesday. I'm doing a not the world's funnest dentist appointment. And so we won't have office hours or class on our next Wednesday. We'll come back a week from today and get going on chapters 20 and 21. But have a great afternoon, folks. If you do have questions, I'll be available for office hours today. And also have office hours on Tuesday and Thursday, just Wednesday for the interruption. But have a great evening, folks. I'll see you all next week. No worries, it happens. I've never had one before, but yeah,
Dentist is always not fun in my opinion.
I agree with you on that. It's just kind of a nightmare, but you gotta do what you gotta do sometimes.
And they numb you pretty good. The numbing just hurts a little bit.
Yeah,
But there's a needle in your mouth, so.
I'm going to Comfort Care Dental, and they're really good about just letting you chill for a while before they do anything after they give you the numbing agents. I've heard horror stories where my sister had a root canal and she said they worked on her too fast and they didn't wait long enough. Jeez.
I have to get laughing gas every time I'm at the dentist, cause I'm always like, please don't touch me.
Yeah, I might actually do that this time.
It's quite fun to laugh. Yeah, so.
Yeah. Well, have a good one.